Hi, it's our pleasure to present our experimental paper. Are we ready for learned cardinality estimation? This is a collaborative work between Fraser University and Tencent. I'm Weiyuan, and in this talk, Xiaoying, Changbo, and I will show you our evaluation on how far are we from deploying the learned cardinality estimators to production. As you all know, machine learning for database has attracted lots of attention these days. For example, in this year's VRDB, we have a keynote from a team, a workshop, and a research session all about machine learning for database. Given there are so many attentions on machine learning for database, we are thinking, what will the world look like after 5 years? In one of the possible futures after 5 years, industrial people gradually lose interest on this topic, and machine learning will not be used in production databases. In another possible future, machine learning is adopted by mainstream databases and greatly improves the performance of these systems. There's no doubt that we'd like to see the second future instead of the first one. However, in order to go to the second future, we need to ask ourselves, are we ready to deploy learned database tuner into production databases? And are we ready to deploy learned index into production databases? And are we ready to deploy learned cardinality estimator into production databases, etc.? In this paper, we focus on answering this question. Are we ready to deploy learned X in production databases where X equals to cardinality? To put it simply, cardinality estimation is a task to predict the number of tuples in a relation that satisfies the predicates without executing the query. We want to focus on cardinality estimation due to these two reasons. First, cardinality estimation is an essential problem but has not been solved in query optimization. Second, recent studies showed that learned cardinality estimation methods achieve impressive results. So, do we know if we are ready for learned cardinality estimation? Our answer is no, due to the following limitations of the existing experiments. First, for all these works, different databases and workloads are used for the experiments. Second, in real world, data update is more common but is less examined in these works. Finally, it is not clear when will these learned methods go wrong. In this work, we are going to do experiments to answer whether we are ready for learned cardinality estimation by answering the following three sub-questions. Are learned methods ready for static environments? Are learned methods ready for dynamic environments? When do learned methods go wrong? The works we evaluated are all recently published learned cardinality estimators. We categorize them into two categories, regression-based and joint distribution-based. The top four methods are regression-based in that they use a cardinality result from a bunch of queries to train a regression model. And then they will use a model to predict the cardinality for a new query. This category is also called query-driven methods. We call the rest three methods as joint distribution-based methods because they try to learn a joint distribution from the existing tables. This category is also called data-driven methods. Next, Xiaoying will talk about more on our experiments.
Thanks, Weiyuan. Next, let me introduce our experiment study and our findings. To ensure fair comparison, we select 4 real-world datasets which have sizes that range from 5 megabytes to nearly 1 gigabyte. They also have various properties in terms of number of rows, type of the column, and size of the domain. Also, each dataset has been used in at least one of the prior work. In terms of workload, we first analyzed the synthetic workloads that generated in existing works, from the perspectives of number of predicates, the operators that they considered, and whether or not to include out-of-distribution queries, which usually leads to zero cardinality results. And then we propose a unified workload generator that is able to cover all workload settings used in previous learned methods. We generate 100,000 queries to train all the query-driven methods and 10,000 queries to test on all methods. The first question we want to study is, are learned methods ready for static environments? In order to answer it, we compare both accuracy and efficiency of learned methods with traditional ones. We use Q-error as the accuracy matrix and show median, 95, 99 percentiles, and max error on all 4 datasets. For traditional methods, we test on 3 popular database products and 6 other approaches that include both heuristic and machine learning-based methods. We compare the 5 learned methods with these traditional approaches under the same size budget. We found that learned methods actually can beat traditional approaches in almost all situations, which shows their potential. Another thing we noticed is that there is a clear winner among all estimators. Naru can achieve the smallest Q-error in almost all settings in our static environment. In terms of efficiency, we compare both training and inference time of 5 learned methods with 3 database systems in order to see whether they can reach the bar in real-world products. For training time, it is clear that all database systems can finish collecting statistics in a few seconds. And other than the method based on gradient-boosted tree, the training time of all other learned methods can be up to 3 magnitudes longer. For inference time, we compute the average latency within the 10,000 test queries. and found that methods built on regression models can actually achieve competitive performance with DBMS products, while methods modeled joint distribution directly upon data requires much longer time. Next, Changbo will show the results for the rest of the experiment.
Thanks, Xiaoying. I'm Changbo. I will start to talk about the second question. Are learned methods ready for dynamic environments, where data is frequently updated? We'll answer this question by two aspects. The first one is, what makes experimental design hard? The second one is, how do learned methods perform? Why it's hard to design a good experiment? Here are some issues we need to consider. When data update, different settings can lead to totally different conclusions. Therefore, we need to consider how frequently does data update, and how the data will change during the update in terms of properties like correlation and distribution. These properties may affect the estimation result. Also, we need to take models update into consideration. Each model may have different ways to update. And when we evaluate the result, we need a metric that considers how long does the model updates, as well as how to measure the combined accuracy of a model before and after the update. We propose a general evaluation framework under dynamic environment that take all issues listed here into consideration. Please refer to our paper for more details. Now, I will briefly talk about how do learned methods perform under data updates. The first table I want to show here represents whether a method or model could finish the update within a small time limit. For example, the first column of census dataset, data will be appended by a batch in every 3 seconds. So the model will have at most 3 seconds to be updated. It means if the model is slow in training, it cannot keep up with the data updates. Each row represents a method. The first 3 rows are 3 database systems. The others are the learned methods. By looking at this table, we found that when data update is very frequent, in many cases, learned methods cannot catch up with updates, but database systems could. In the second table, we give a longer update limit to make sure all the learned methods have enough time to finish their model update, and show the accuracy rank. In the table, 1 means the best accuracy, 5 means the worst. We can see that weighted XGB performed the best in census and forest datasets, and Naru performed the best in power and DMV datasets. We can see there is no clear winner within the learned methods in dynamic environments. The observation is different from static environment, where Naru is the best in all the 4 datasets. Next, I will answer our third question. When do learned methods go wrong? During our experiment, we identified some illogical behaviors from the learned method. Here we show 2 examples. The first example shows the estimation results are not monotonic. In the 2 example queries, the only difference is that query 2 has a smaller range predicates than query 1. So the cardinality of query 2 should be smaller or equal to query 1. However, the actual estimation result of query 2 is 61% larger than query 1. Another example shows the estimation result can be very unstable. When we apply a learned method on the same query for 2000 times, we plot the distribution of the estimation results. This estimation can range from 0 to almost 6,000. These illogical behaviors caught our attention, since they may hurt the trust of database developers, and thus make it harder to really deploy the new learned methods into production. We summarized these observations into 5 intuitive logical rules, and found that, other than DeepDB, all learned methods violate some of the rules. We hope these rules could also guide some future design in the learned cardinality estimation research. For example, applying some constraints to the model architecture or in training and inference stage to force the prediction become more logical. To conclude our work, we would like to answer the big question. Are we ready for learned cardinality estimation in production? The short answer is not yet. The long answer is that through our comprehensive experiments, we show that learned methods show great accuracy in static environment. However, these learned methods have some key drawbacks. The first key drawback is that comparing with traditional histograms, they are costly. More particularly, they tend to be low speed in training and inference. Also, in order to train good models for different datasets, the cost of hyperparameter tuning is also expensive. And when dealing with frequently updated data, these models cannot do well. Another key drawback is that learned methods are hard to be trusted. First, current models are mostly black box and are very complex. It makes them hard to understand and debug. The second reason is that they have shown illogical behaviors, which are random and unpredictable. So in order to maximize our research impact, we need to address these 2 points by making the learned methods less costly and more trustworthy. It will introduce us a world where ML is deployed in DB productions. Thank you for listening. Please find more details in our paper. Our GitHub repo is available. It's called RCE Learned It, and we are happy to take questions. Thank you.